So this is chemistry starting unit 8. In this unit, we're going to start talking about chemical reactions. So first question is, what is a chemical reaction? A chemical reaction is a process in which the atoms of one or more substances are rearranged to form different substances. A substance in a chemical reaction undergoes a chemical change, and this part is important. It becomes an entirely new and different substance. You'll see this as we go throughout the unit. It has to be new and different. This excludes some things, like if you have a piece of ice that melts, it's kind of new, but it's not a different substance, and so that doesn't classify it as a chemical reaction. As we go through this unit, you're going to have to think critically about some of these things and question, did a chemical reaction really occur, or could I explain this in some other way that's maybe a physical change? So whether you think about it or not, you see chemical reactions every day. For instance, photosynthesis. It's used by plants. Carbon dioxide and water undergo a series of chemical reactions, and they end up producing glucose to power the plant, and oxygen is a byproduct that we use ourselves. When you eat, the point is to convert the food into energy. This is an example of a reaction where the energy is what we want, not necessarily the products. Riding in a car or truck, the engine, it's converting the fuel into new products. Yes, things like CO2, H2O, CO, things that we don't really need. But again, it is the large amount of energy that we're interested in. The battery in your phone, it's producing a chemical reaction. So this chemical reaction is also concerned with energy. Electrons are moving from one reactant to the other. The energy is being transferred. Eventually, the reaction stops because it ran out of reactants. And so you plug it in, the electricity flows backwards, and the chemical reaction is reversed. This is a chemical reaction where it will go on its own, but if we put energy into it, we can make it go backwards. This is the way it works with a pretty big number of chemical reactions. Given the right amount of energy, we can reverse them. So how do we know that a chemical reaction has occurred? First, a couple of terms. We have two basic types of substances in the chemical reaction. We have reactants and we have products. Reactants are present in the beginning of the chemical reactions. A lot of times they're solutions. They are something dissolved in water. The products are produced by the chemical reaction. Some of the easiest chemistry terms you'll come across. Reactants react, products are produced. For some chemical reactions, we can tell pretty easily that a chemical reaction has occurred. However, not every chemical reaction results in an explosion. Some chemical reactions require us to pay attention to smaller details. So in chemistry, we're looking for evidence that a chemical reaction has occurred. A lot of times, physical changes will accompany chemical changes. Maybe there's a change in color, or maybe things are changing state, liquid, solid, gas. When two substances are combined and a dramatic physical change occurred, a chemical reaction may have occurred. So the first one of these pieces of evidence is a color change. A color change is a pretty good indication that a chemical reaction may have occurred. For instance, a nail that gets left outside for a long period of time. It may turn from gray, that metallic color, to reddish brown. The color change indicates that a new substance formed. Rust is a new and different substance than, say, the iron that made it. It really doesn't even take a long time. So I said for a period of time. I recently left a nail outside and it rained, and within 3 days, this chemical reaction happened. The entire outer layer of the nail was now rusted. It does not have to take a long time. If you mix two substances, two solutions, a color change might indicate a chemical change. For instance, if we combine two colorless solutions, so colorless is the color of water, basically. Most people would say it's clear. Clear is more of the property of how well can I see through it. For instance, blue Gatorade in a glass, if I can see through it, it's still clear, but it's blue, it's not colorless. Water is both clear, you can see through it, and colorless. This is the color. Sidebar. If you combine two colorless solutions, a different color is a good indication of a chemical change. But we have to be careful. We need to pay a little bit of attention. Use a little bit of our critical thinking skills here. Not every change in color indicates a chemical reaction. For example, if you walk down a long hallway to your art class, if you have blue paint and you have red paint, when you mix them together, you get a different color. It's going to make purple. It's not a chemical reaction. Red and blue, when you mix them together, pretty much expect to get purple. Same thing if you mix red Gatorade and blue Gatorade. You expect to get purple. Purple is what I would call an expected color. We are more concerned with unexpected. So if you mix two colorless things and you get red, if you mix red and orange and you get yellow, those don't quite follow what we would expect. That is what we're looking for. Second piece, a temperature change. A temperature change is an indication of a chemical change. So think about two substances and they're both at room temperature. And to define room temperature, it's approximately 20 degrees Celsius, which for most of you we're going to say is about 72 degrees Fahrenheit. RT, room temperature. If no chemical reaction occurs after we combine them, the substances are both going to remain at room temperature. We should not see any sort of a change. We shouldn't mix two things and increase the temperature if nothing happened. If a chemical reaction occurs, the temperature may increase or it may decrease. It's not really limited. A lot of times we think of like an explosion, fire, it's a chemical reaction. It gets hot. But you can have other reactions where things are decreasing in temperature. Sometimes the temperature change is enough to feel through the container. Those are usually pretty dramatic. Other times you may have to measure it with a thermometer. Qualitative data, quantitative data. So here's an example of a temperature change that does not indicate a chemical reaction. If you add ice to a drink, if you add ice to a drink, it will decrease the temperature of the drink. I'm going to draw you a diagram here. Here's my drink. Here's my ice cube. The temperature of the drink, we'll say, was 20 degrees Celsius. The ice is 0 degrees Celsius. Room temperature, freezing. So what's really happening here is thermal energy moving from the drink to the ice. What is happening is this ice is pulling the heat out of the drink. It's pulling the heat into the ice. This is not a chemical change. The ice will most likely disappear. That's a physical change. That's a change of state. Next up, production of a gas. Production of a gas can indicate a chemical change. How do we observe production of a gas? Generally, we're looking for bubbles. There are some reactions where you can physically see the gas. But producing bubbles is the easiest way. It's the most common way to see that a gas is being produced. It's going to require something, though. At least one of the substances has to be dissolved in water, or possibly some other kind of liquid. Here's your 5th grade science example. Think about a baking soda and vinegar volcano, which none of you have probably actually made. One reactant is baking soda, and it has a chemical formula. It is an ionic compound. We call it sodium hydrogen carbonate. But this one's a solid. It's a powder. You're pouring it, but it's a powder. The other reactant is vinegar, which is actually known as acetic acid, HC2H3O2. It's a solution. When we combine them, both substances become part of the same solution. They're all mixed together, they're mixed in the water, then the chemical reaction starts. If you had both of these things in powder form, nothing would really happen. This reaction produces a large amount of gas, which we observe as bubbles. Another possibility, and this goes along with the production of a gas, production of an odor could indicate a chemical change. If two substances are combined and produce a new and different odor, a chemical reaction may have occurred. So here's a generic example. Gasoline and diesel fuel both have unique odors. You could do a blind test and say, I smell this, yes, it's gasoline. Some of you could do the same with diesel, maybe not as many. So gasoline has this really unique odor, and then it's burned in a vehicle's engine. Products have completely different odors. Unless you have a really old vehicle that the exhaust smells like gasoline, that's an inefficient engine, they're going to have different odors. Most modern cars, you're not going to smell gasoline in the exhaust. And generally in this class, we want to avoid making observations by smelling them. It's known as your olfactory sense. It's a bad habit. Deliberately breathing gases, for one thing, it's dangerous. Second, it's a bad habit in the laboratory. It's been done before. Every chemical, every gas out there has been smelled or inhaled. There's no scientific basis for us to smell any of these on purpose or breathe them in on purpose. We know the effects. If both the substances are dissolved in water, we may end up with a solid product. When we get a solid from two solutions, it is known as a precipitate. A household example is milk curds, which in Indiana we typically know this as cottage cheese. Milk curds are produced by adding an acid to milk. There's other ways to do it, but this is one. The acid reacts with the milk proteins. The proteins were soluble in water. The new product is no longer soluble. It forms a solid precipitate. It sinks to the bottom of the solution. A precipitate, important to note, not the same as freezing. Freezing is a change of state, which is a physical change. This is where you lower the temperature of something until it becomes a solid. Temperature is unrelated to the formation of a precipitate.